Welcome back to the classroom. My name is Mr. Wong, and today we're going to be looking at a past paper question from Module 4, Inquiry Question 1 for Physics. This is on electrostatics, so let's have a look at what the question's asking and how should we approach it. So, in this diagram here, we have the centers of two small positively charged objects separated by 20 centimeters as shown in the diagram below. This is positive 2 microcoulombs, and over here we have positive 4 microcoulombs separated by 20 centimeters. On the diagram, we need to draw the electric field lines. Now I know because we have two like charges will repel. So like charges repel. And we can sort of imagine there's sort of like an asymptote line in between here where the electric field lines will not cross over. Okay, so we've drawn the scenario here. What I also can say is because it's positive charges, electric fields always go from positive to negative. That's kind of what we're trying to show for here. So we can draw lines from the positive 2 charge, and it goes away here. It can go here, down like so. And as you can see, I'm trying to represent the fact that it is not going to go past this line. And then I can show lines going out this way and lines going out that way. Okay. I can show a similar thing here. Obviously, if you can draw better than I can, that would be awesome. So it goes that, goes away, goes away. There is a second part to this, and it's to do with the charge of the particle. The greater the charge, the greater density of the field lines we would experience. So given that plus 4 is twice as large as plus 2, instead of having 4 electric field lines, I'm going to draw 8 lines to represent the field strength of my positive charge. Okay, and that's how you would complete this question here. Moving on to question B. It says we need to calculate the magnitude and direction of the electrostatic force between the two charges. Okay. So the formula that I'm going to use is F equals to 1 over 4 times pi epsilon naught Q1 Q2 over R squared. Okay, now just for people's simplicity's sake, I'm going to just write down a couple of things. I know that Q1, and it doesn't really matter which one we decide is Q1, is 2 times 10 to the power negative 6 coulombs. That's how many microcoulombs is in a coulomb. Q2 is 4 times 10 to the power negative 6 coulombs. You could potentially even write them down as positives if you like to help you remember them. I know that R is 20 centimeters, so I need to convert that into meters. That would be 10 to the power negative 3 meters. Okay, and then the last one is this epsilon naught here. This is given to you on your data sheet, so you can work it out from the data sheet. So quickly sliding into the physics data sheet, you can see epsilon naught is this point here, the electric permittivity constant, and it's given by the following value here, so 8.854 times 10 to the power of negative 12. Okay, so I'm going to put that down in my formula here. Okay, I'm not going to write out the units here because I'm going to run out of space. But do remember the whole concept of epsilon naught has two purposes. One, it's to describe how electric fields are projected in a vacuum. And also it is to give us the units for force. Okay, So what I can do now is do my substitution. Hopefully I have enough space to write all this down. So just write that down there, times 10 to the power of negative 12. Okay, the charge I have, 2 times 10 to the power of negative 6. That's a positive value. And then we have 4 to negative 6. And that's 20 centimeters, or once we convert that into meters, that should be a 2, not a 3. Okay, now let's substitute that in. Before we do, let's not forget to put the square there. Okay, so I get a value of 1.79 if I just write down the entire numerical value. That's what we have here. If I look at the amount of significant figures asked of me in this question, technically speaking, you can have the 2 and the 4 there. We have the 20 centimeters there. So technically, in the calculation, it should round off to 1. But obviously, it's a little bit weird to write it as 2 newtons because it's quite off. So I'm going to round it off to 3 significant figures here. So 1.80 newtons. And in terms of the direction that we have, it is an attractive force. So it's an attractive force, or sorry, it's a repulsive force. Repulsive force. Both charges move away from each other. So both charges push away from each other. And that's how you do the question for electromagnetic fields. Technically, we're using Coulomb's law here. So this is how we present electromagnetic fields up here. And this is how we can apply Coulomb's law to calculate the force applied by 2 charged particles. If you found this video useful in developing your understanding, or perhaps your approach in exploring the ways of answering exam problems, hit the like button and subscribe, and I'll see you next time.